One of the interesting things about computing that has added to how we understand some mathematical things and has used mathematical things to help us compute better is the problem of representing numbers inside a machine. So when we look at a number like 98, it's actually very difficult to understand what this means. It doesn't seem difficult because we've all been doing it for literally for decades as individuals and for centuries as a species. And so what we have here is that this is a base 10 representation, and the the situation is that 98 is actually it's a place, right? So 9 is 9 times 10 to the 1. 10 to the 1 is 10, so that's 90. And then we have 8 times 10 to the 0. 10 to the 0 is 1, so that's 8. So 98 is 9t, excuse me, plus 8. And we've been doing this so long that it doesn't seem difficult, but in fact it is. This is a very difficult situation from a computational perspective. Many older computers actually tried to work in base 10. They wasted a lot of space, they wasted a lot of time. It seemed easier for programmers to put things down in base 10, but the computers were much faster and more efficient and able to handle much more data by switching to base 2, to binary. And so what happens in base 2 is that it's still a placeholder system, but what you have is a binary number, let's say 1011. And what this means is that we're going to have some expansion in terms of powers of 2. Lots of things happens in terms of powers of 2. So the powers of 2 here are 0, 1, 2, and 3. And so what we have here is 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1. 2 to the 1 is 2, but that evaluating that destroys the pattern, and we're much more interested in the pattern right here. And then we have 1 times 2 to the 0. And in fact, what we've kind of done here is we can kind of nest these things where the order's kind of gotten reversed. So we've gotten accustomed to writing things in a certain order, and it's a little bit harder. So a picture like this kind of shows what happened in here and where they ended up in here. So there, you might have heard about conventions about big endian or little endian numbers. Is the first part the thing that you see, the biggest, most significant bit or most significant digit, or the least significant bit or digit? And so so those are different. Hardware is based on different uses of that convention. As long as the hardware is consistent with itself, then that's not a problem. Okay, so what we have is, let's see, let me actually do the arithmetic here. I've got 8 plus 0 plus 2 plus 1. So in our base 10 system, that's what we call 11. And it's also sometimes useful to think of that in base 16. 16 is hexadecimal, and the hexadecimal equivalent here is C. So C, because you have 9, and then 10 is A, 11 is B, 12 is C. I guess it's B, sorry. My error. Okay. So it's B, base 16. It sounds like a vitamin, doesn't it? Okay. So the reason that we like binary for computing is what this thing that we came up with in talking about sets, which is the exclusive OR. So remember, exclusive OR means something is in one set or another set, but not in both. And one way, if you think about a bit representation of membership of sets, like happened in the last video, you get a 1 and a 0 in one set, not in the other. That means in the exclusive or you get a 1 and a 0 in one set, not in the other. That's the exclusive or. But if it's in both, 1, 1, then you're not in the exclusive or. And so, and that's addition. If you look at 0 plus 1, that's 1. And if you look at 1 plus 0, that's 1. I'm using, third grade notation here. And the thing is, if you look at 1 plus 1, that is 0 with a carry. So as terms of addition, 1 plus 1 is 0 with a carry. In terms of exclusive or, the exclusive or of being in both sets in the intersection is it's not in the exclusive or, and so that's why we've partly why we settled on base 2 for computing. It's easy to design circuits to do this kind of stuff very quickly in hardware, and so that's what we've got. The problem is, if I give you a number like 98, or you give me a number like 98, and I want to get it into the machine so that the machine can operate on it, it needs to be converted into binary, into base 2. And so there's an algorithm for doing this that is a very interesting algorithm, and actually points to a lot of things that happen in computing as you move on with this. Is, first of all, it's a recursive algorithm. You do something that cuts down the size of what you're working on, and you repeat on the smaller one. You do something, cut down size, repeat on the smaller one. Now, these things getting smaller, that process does have to terminate, and so we have a recursive algorithm. A lot of times recursive algorithms are conceptually easy, but slow, inefficient. But this one is actually conceptually correct and works pretty quickly, and so it's something they get used all the time. So what I'm going to do is I'm going to first write down the algorithm in kind of a symbolic way. I'm not going to put in all the parentheses and things, but and then we're going to do it. We're going to do an example. So the algorithm is this. What we do is we take the number that we have and we divide it by 2, and we look at the remainder. The remainder is going to be 0 or 1, and so that's the bit that gets thrown off by this part of the operation. Some people call that mod. That's built into a lot of computer languages. It's built into a lot of hardware sets, and so we're going to take the number x mod 2. So what we're going to have is we're going to have x mod 2. Let's give this algorithm a name. Let's call it D2B. D2B for decimal to binary. Decimal to, like Gleek speak, binary. Okay. So what this algorithm does is you divide by 2, and then you take the remainder. That's the bit that gets sent out. And they're coming out in the opposite order. We have to be aware of that. And then you apply the algorithm. So D2B applied to. And now what you do is, it depends on your perspective in life. One thing that you can do is say you're going to divide by 2. Another thing you could do is say shift to the right. That would be the right in the kinds of machines that we have. So that's the algorithm. And I've used this pretty common symbol that you've already seen for union, but it's also used for this, for concatenation. Concatenation is just jamming things together. So there's the algorithm expressed symbolically. Okay, so let's do it. And I started to talk about 98, so let's do it to 98. And so what we're going to do is take 98 and divide it by 2. And 98 divided by 2 is 49. We're going to need that. And the remainder is 0. So the bit that gets thrown off by this, thrown into the pile by this step, is 0. That's in green. And then we have 2 times 49. And 49 is the x over 2 that came in my representation of the algorithm. And so now I'm going to do the same thing to 49. And 49 is much more interesting because it's 2 times 24 plus 1. So let me write that in, 2 times 24 plus 1. So now we're getting a 1 out of the algorithm. So 2 times 24 plus 1. And then we do the same thing to 24. I'm going to kind of shortcut that one a little bit because 24 is 2 times 12. And then, wait a second. 24 is not 2 times 12. We're interested in the remainder. We want to write down the remainder explicitly. And so it's 2 times 12 plus 0. That keeps the pattern going. And then the next one that we would have is 12. 24 divided by 12. So 12 is 2 times 6 plus 0. It's not adding an extra step to write the plus 0. It's skipping a step to not write the plus 0. So keep that in there when you're working on some of these. And then we've got, well, let's see, 6 is 2 times 3 all together now plus 0. And 3 is 2 times 1 plus 1. So we've just kind of worked our way down. And the last one is the quotient there was 1. So 1 is 2 times 0 plus 1. It's not 1. 1 is not 1. 1 is 2 times 0 plus 1. That indicates that we've terminated the algorithm. And so the equivalent of 98 is 11000010. This is the most significant. This is the least significant. And if we check on that, let's see, let's write out some powers of 2 here. Powers of 2 are 1, 2, 4, 8, 16, 32, 64. And so what we're seeing is where the coefficients of 1 occur are at 64 plus 32 plus, I'll skip a few because they're 0 so they don't change the value, plus 1 times 2. So these are all the zeros. I've just put the ellipsis in there. And 64 plus 32 is 96, plus 2 is 98. So we found the binary equivalent. I'll put it in the box here. And this is now something that we can put in the box and add it to other things that we put in the box and actually get some good computing done.